Hello, everyone. I'm Jesse. This is my 2025 data mining project, known as TEAL, which is the Tactical Evolutionary Analysis of the Clash Royale ladder. To start, I'm going to introduce the team. We have Jesse Retro Dong, who is a data engineer. We also have Jesse Access Denied Dong, who is the model lead. Um, we also have the Brains, which he was responsible for the evaluation and visualization lead. And we also have Shadow, which is the systems and optimization lead. So first to explain what the game is about. Clash Royale is a 1v1 mobile game where people battle with a deck of 8 cards. So there's 16 cards in total. Um, on the left side is a screenshot of my own deck, and on the right side is a screenshot of what an actual game might look like. So we have the top Elixir bar on the top and the bottom of the screen, and people expend cards in this grid arena. So in regards to the mission, my goal for this machine learning project was to find and predict the win rate of any deck, and also to find the best Clash Royale deck possible. So the first step that I needed to go through was to first collect the data. And so this data was accessed through the official Clash Royale API. And so I specifically filtered the game modes. I only chose the ranked 1v1 mode, and this way there wouldn't be too much noise. If there were other game modes, the optimal cards would be different for each game mode, and so it would add just a lot of noise. Um, and I would also strictly filter for wins or losses. So there's a rare chance where players will draw. Um, and so I took these out and I only looked for wins or losses. And in regards to the scale of the thing of all the data that I collected, there was a total of around 55,000 battles. And from these battles, I found 3,000 plus unique players. Um, Within this, there was 121 cards, which is the maximum amount of cards within the game that people can use. Um, and the baseline win rate was around 60%. And in regards for the collection method, I first filtered for top clans, and then from those top clans, I would check the players within these top clans or like these top groups to find or to train my data on strong players. So here's a screenshot of my CSV file and what it looked like. So on the left side, we have the player tag. This is just to make sure we don't have repeating players. And so for each player, the API would save up to 30 battles within their account. And so there were many battles here. Um, if you look to the right, we also have the ranked 1v1 arena, which kind of just is the mode to make sure we don't have like one of the irrelevant game modes. And then on the very right, we also have the deck. So these are the actual cards that the player used, and also I also saved like what card the opponent used. And at the very end, the result is going to be either a win or the loss. So now that I have all this data, I tried in total 4 machine learning approaches. So logistic regression, neural network, kernel methods, and decision trees. So the baseline, like I mentioned earlier, is a 0.604 true win rate. So from all the battles that I collected, this was the true win rate. And then we also have the AUC, which is zero point 0.5. This stands for area under the curve, which just tells us how often it assigns a higher score to a win compared to a loss. So for logistic regression, the very first model, I was predicting the probability of wins given the decks in the match or given the 16 cards that were used within the match. And this is actually the probability that I'll be predicting for across all models. For the linear model, it was set on 242 features. 242 comes from 121 card options. So each player has 121 card options, and they can have 2 decks in total. There's like the own player's deck and then the opponent's deck. So it's 121 times 2. And for the accuracy, I got a 0.552 AUC, which is not super notable. The baseline is zero point 0.5, which means like that's what happens if we always predict a win. And so this kind of just shows there seems to be limited signal at least within the simple model. So then I moved on to neural networks. Um, so from the neural network, I captured, or this captures nonlinear interactions between the cards and the deck matchups, which seem to be a lot more promising. I tried two approaches. I first did two hidden layers, and then I tried three hidden layers. Um, but for the third, the model with three layers, the AUC decreased. Um, and so just stuck with two hidden layers. From the results from the AUC that I got at the very end, I got a 0.567, which is an improvement compared to logistic regression, but still not super notable. And it kind of just indicated that even though a neural network is a flexible model, it doesn't seem to overcome the noise. So the next method that I used, this is the third method, was kernel methods, um, using a RBF support vector machine. Because kernel methods are a lot heavier computationally, instead of using 55,000 battles, I just took a subsample of 15K battles. And this is just to improve the runtime so I don't have to wait for like hours upon hours end. Um, Within kernel methods, it implicitly maps decks into a higher dimensional feature space, um, which seemed to be promising. But unfortunately, similar to the other fate of the two different approaches, the AUC was 0.53, so very, very close to the baseline. And then finally, as like a last attempt, I tried decision trees. So specifically, I used XGBoost, which is a gradient boosted decision tree. Um, this was naturally modeling card interactions and also nonlinear splits. So saying that card X, or saying the deck has card X and also lacks Y. For this one, it did have the best AUC, so it was at 0.57. But in total, all these kind of just confirm that deck composition do contain signal, but it doesn't seem to be enough data or enough features to predict win rate by itself. So here's a total comparison. We have accuracy and AUC as the two columns, and we can see from the baseline we have 0.604 and zero point 0.5, and the rest of the values. So this is what it looks like on the ROC curve comparison. The dotted line is a baseline. We can see at the very top it's decision trees with a 0.582 AUC, but nowhere near the amount of curve that we want. It's nowhere near the one true positive rate mark. I also created this plot of the top 20 card importance. So this ranked the cards like weight from the decision trees. And we can see at the very top, we have Firecracker, Tesla, Three Musketeers, etc. So after attempting to predict win rate, but not being able to be so successful, I tried to pivot instead to a evolutionary algorithm. So this was trying to calculate what is the best optimal deck within these 121 cards. So from this, instead of using XGBoost, I actually used the neural network approach, which seemed to give me the highest win rate. Um, from the evolutionary algorithm, it seemed to converge after 30 generations. Um, and so I'd run this program, like I would run one cycle of the evolutionary algorithm, and this would be containing 75 generations each, and I would do this 50 times in total. So interestingly enough, some patterns I found was that the barbarian barrel and also cannon cart seemed to be reoccurring. So there did seem to be like a noticeable trend. And comparing this to player data or player analysis, barbarian barrel is considered a S tier card, which seems to indicate that at least to some extent, the models or the neural network model has some significance. Yeah, and so this is actually the best deck that I found. So this deck had a fitness of 0.866, and it includes Barbarian Barrel, Bowler, Counter Cart, Elixir Golem, Heal Spirit, Inferno Tower, Rascals, and Expo. And I actually played with this deck to test to see if it was really valid. Unfortunately, the deck was not quite as well as I thought it would perform. It was kind of subpar within battles, and so it didn't really work out. So now talking about the limitations, which I have many. Um, So because this data is trained on the collateral API, um, all the decks that I used were at the high level ranked 1v1s. But something I noticed was that because they're already at this very high level, it seems that the wins or the losses is more dependent on skill rather than the cards themselves. And this is because in order to get to this high level, you would have to have already a valid deck. In addition, for the data limitations, there weren't evolutions, which is another feature within cards. There weren't tower troops, which missed more features. Um, it's also strictly a win or a loss, so it doesn't include the draws that we talked about. And there's also no in-game tower damage, which says like how much a person won by. Um, and then also it doesn't account for lag or people leaving games. So yeah, like I mentioned before, I had played a couple games with the evolutionary algorithm deck, and even despite playing, it still felt weak. So finally, my main takeaway was that deck alone is not a strong predictor. It's actually a weak predictor for win rate. Um, and because of this, we need more features as there's too much noise. So if the data is bad, there's no model that is able to perform well. And in general, the evolutionary algorithm cares more about the top extremes. Um, so in this case, neural networks seem to fit better than XGBoost. That's my presentation. Thank you very much for listening.